14 kilometers of water. That's all that separates Europe from Africa. It seems that if people can build tunnels under seas and construct bridges stretching tens of kilometers, this should be the easiest place to do it. But this is one of the most difficult places on the planet for construction. Here, two oceans collide, creating underwater whirlpools so powerful they can tear out multi-ton concrete supports. To build this bridge, you would have to conquer a depth of 900 meters. That's 3 times the height of the Eiffel Tower. Add to that the strong currents constantly pressing against the structure with tremendous force. Today, we'll break down this insane project and understand why even the world's best engineers still can't handle 14 kilometers of water. By the end, you'll learn what discovery on the seabed of the strait makes building this bridge physically impossible. Imagine standing on the Spanish shore in Tarifa and clearly seeing the white houses of the Moroccan city of Tangier. It feels like you could reach out and touch them, but this illusion has misled more than one generation of builders. As you look at the horizon, hundreds of drivers in the port of Algeciras pound their steering wheels in frustration, losing a second day in the ferry queue. The logistics of 2 continents today resemble a broken clock. Trucks loaded with African vegetables and European electronics come to a halt before 14 kilometers of water, turning a short route into an exhausting marathon. Every hour of delay burns thousands of liters of fuel and millions of euros. A bridge could become a goldmine, turning this chaos into an endless conveyor, moving at a speed of 120 kilometers per hour. The race to conquer Gibraltar began back in the 18th century, when engineers, armed with their first drawings, tried to convince monarchs that the project was real. In the mid-20th century, officials from Spain and Morocco moved from words to action. They formed working groups, sent out research vessels, and began drilling the first test boreholes. Routes for future highways appeared on maps, and politicians prepared for the official launch of construction. But as soon as the heavy drills touched the seabed, enthusiasm gave way to trevoga. Equipment broke down, and the data from instruments showed numbers that didn't fit into any construction textbook. Do you think the main problem is money? In reality, investors have long been ready to write a check for any amount, but over hundreds of years, not a single architect has dared to put their signature on the final design. Today, the situation in the strait has reached a boiling point. While government offices in Madrid and Rabat continue to study bridge proposals, a real battle with the elements is unfolding on the water. Ferries storm the waves, trying to carry at least a fraction of the massive flow piling up on the shores. If one of the ships breaks down, the transport system of an entire region comes to an instant halt. Massive trucks are forced to turn around and take routes thousands of kilometers long, skirting entire seas just to avoid sitting in this enormous traffic jam. But why, after building bridges across entire bays and tunnels under straits, do we still hesitate here? Look around. On the surface, everything seems calm, but beneath the keel of every vessel lies something capable of turning a steel support into splinters. Very soon, you will understand what exactly made the world's best engineers retreat from this coastline in fear. To grasp the scale of the problem, imagine Gibraltar not as an ordinary strait, but as a place of constant collision between 2 water giants. Here, the cold waters of the Atlantic Ocean meet the very salty, dense waters of the Mediterranean Sea. Because of the difference in density, they cannot simply mix. The heavy, salty water from the sea sinks to the bottom and flows out into the ocean, while the lighter ocean water moves above it in a powerful counterflow. As a result, at the same point in the strait, the water moves in 2 opposite directions at once. The upper layer, hundreds of meters thick, rushes one way, while the lower layer moves the other. This phenomenon creates a tremendous load. Any vertical support in these waters would literally be crushed. If you place a long steel pillar into the water, its upper part will be pulled eastward with great force, while the lower part will be dragged westward. Imagine a massive structure being torn apart or twisted in different directions every second by two invisible hands. The speed of these currents reaches 4 meters per second, which is enormous for water. Tons of liquid press against the piles with such force that ordinary concrete would begin to break down within just a few months. The internal waves are so powerful that they can throw multi-ton submarines up and down by dozens of meters, knocking them off course. However, the most frightening detail lies deeper and is completely invisible from the deck of a ship. In Gibraltar, there are so-called internal waves that form exactly at the boundary between two layers of water with different densities. The surface may be perfectly calm, but at a depth of 300 meters, underwater mountains rise to heights of over 100 meters. The giants move beneath the ocean's mass, carrying colossal energy within them. When such an invisible wave strikes a bridge support, the force of the impact is comparable to a collision with a multi-ton train at full speed. These waves arise due to irregularities in the seabed, turning the space between the shores into a zone of constant hydraulic shocks. The situation is made even more complex by the fact that these processes are completely unpredictable. Research instruments installed by scientists for measurements often simply disappeared or were recovered broken. In some areas of the seabed, deep grooves were discovered, carved by powerful currents that move massive boulders as if they were small pebbles. Nowhere else on the planet have bridge builders faced such a combination of depth and chaotic water movement. Add to this the constant whirlpools, and it becomes clear any standard support would become a target for this hydraulic hammer. Many believe it would be enough to create ultra-strong piles, but in Gibraltar, there are no calm zones. Even at the very bottom, the water never stands still for a single second. Engineers have calculated that the total pressure on a bridge structure would exceed the limits for the strongest materials in the world by dozens of times. Every design that looked perfect on paper was deemed unworkable after the very first tests in a water chamber. We are used to thinking of water as a yielding medium, but here it behaves like a solid and relentless press. However, as it later turned out, even these currents were only the beginning of the problems. The real dead end for the builders came when they studied the very terrain of this underwater gorge. It turned out that the seabed of the Strait of Gibraltar is nothing like a flat surface where a foundation could be calmly built. Imagine a gigantic underwater canyon with steep cliffs and sharp rocks. At its narrowest point, the depth reaches 900 meters. To grasp the scale, that's 3 Eiffel Towers stacked on top of each other and completely hidden in the abyss. Even at the shallowest section, the Camarinal Sill, the depth is 300 meters. Can you imagine a 100-story building standing on an uneven rocky slope in total darkness? The main dead end for builders is installing the supports. A typical bridge requires massive concrete columns firmly anchored in solid ground. But there are no technologies in the world capable of securing such a structure at depths of hundreds of meters in raging currents. It's not just about and the column would simply snap under its own weight. How do you lay a foundation where even research robots struggle to hold their position? The famous Akashi Kaikyo Bridge is often cited as an example, but compared to Gibraltar, the Japanese project looks like a walk in the park. There, the sea depth under the supports is only 60 meters, 5 times less than at the most favorable location in Gibraltar. The experience of Turkish or Danish builders is useless here as well. It's as if we are trying to build a true skyscraper using the rules of assembling a children's construction set. The combination of vast distance and extreme depth makes all existing global experience simply irrelevant. What ultimately undermines the project is the structure of the seabed itself. Preliminary studies have shown that the bottom here is covered with layers whose nature sparks intense debate. Building on such a foundation is like placing a heavy wardrobe on a mattress filled with sand. The support must stand motionless for decades, but in the strait, the seabed itself presents surprises that cannot be ignored. Engineers have encountered a set of natural traps, each of which on its own makes construction impossible. Standard methods don't work here, and this has forced scientists to propose ideas that sound more like plots from science fiction films. But before building floating bridges above the water, engineers had to face another threat. Ready to find out why this project could collapse because of processes taking place deep within the planet itself. When the classic blueprints with concrete supports were thrown into the trash, engineers proposed ideas that 30 years ago would have been called madness. If it's impossible to rely on the seabed, the idea emerged to make the bridge float. One of the most discussed concepts was a floating bridge on giant pontoons. Imagine massive blocks the size of houses. They hold the roadway like floats on a fishing line. It seemed like the perfect solution. There's no need to dig into rock at a depth of 900 meters. But as soon as mathematicians began their calculations, optimism quickly gave way to new concerns. The problem came from where no one expected it. Gibraltar is one of the busiest sea routes in the world. Every year, tens of thousands of massive tankers pass through these 14 kilometers. A floating bridge would become an insurmountable physical barrier for them. Any navigational error or engine failure on a vessel weighing 300,000 tons would turn such a bridge into a pile of scrap metal within seconds. In addition, the pontoons would have to be anchored to the seabed with steel cables as thick as an adult human torso. Under conditions of constant chaotic water movement, these moorings would be subjected to extreme loads that cannot be controlled. Then another project was put on the table, a suspension bridge with record-breaking spans of 5 kilometers. To support such a massive structure, towers over 5 feet high would be required. That's taller than many modern skyscrapers. But here, engineers hit the limits of the materials themselves. It turned out that steel cables under such weight would begin to stretch and lose strength simply under their own mass. We have reached the point where metal stops being reliable. If the cables are made even thicker, they become so heavy that the structure would collapse under its own weight before the first car even crosses it. After that, attention shifted to an underwater tunnel. If it's impossible to go over the water, the idea was to dig beneath it. This would solve the problem of storms and massive ships on the surface. The Afri Tunnel project was developed to lay a railway under the strait. But Gibraltar is not the English Channel. Beneath the water. Here, preliminary surveys showed that the composition of the rock changes every 100 meters. Massive machines worth hundreds of millions of dollars risk simply getting stuck in a heterogeneous mass that cannot be predicted in advance. Every new solution runs into a physical barrier that cannot be ignored. We create ultra-strong alloys, but Gibraltar always seems to stay one step ahead. And while the best minds on the planet argue about cable thickness, the very ground beneath the strait is preparing a surprise they cannot calculate their way out of. Have you ever wondered what happens when two massive continents move toward each other exactly where you've decided to build a bridge? When engineers figured out how to deal with the currents, nature presented them with the biggest surprise of all. It turned out that the Strait of Gibraltar is not just a crack in the earth, but a place where two giant parts of the planet collide directly. This is where the boundary between two massive lithospheric plates runs, the African and the Eurasian. The most alarming part is that these plates are not standing still. Africa is slowly but steadily moving north, literally pressing into Europe. The speed of this movement is small, just a few millimeters per year, but for a rigid bridge, it sounds like a death sentence. Imagine building a 14-kilometer bridge while the shores it's anchored to are constantly creeping toward each other, trying to crush the structure. This plate movement creates another danger: high seismic activity. The region of the strait is regularly shaken by earthquakes caused by accumulated stress in the Earth's crust. In the history of this place, there have already been disasters that wiped entire cities off the map. If a conventional rigid bridge were built here, the first serious underground shock would turn it into a pile of shattered concrete. During an earthquake, the supports on different shores would begin to move in opposite directions. Creating a structure that is flexible enough to withstand such impacts and at the same time strong enough to carry thousands of tons is currently impossible. But even if we could protect the bridge from earthquakes, a new problem would emerge, hidden in the seabed itself. Detailed studies have shown that it consists of extremely treacherous and soft sedimentary layers. In reality, it resembles a thick, sticky mixture of clay and sand that extends hundreds of meters downward. Trying to install a heavy support on such a foundation is like trying to plant a steel rod into a swamp. It will slowly, but inevitably, sink downward. These layers of soil change their properties under water pressure or even the slightest vibration. How can you build something permanent where the very ground beneath your feet behaves unpredictably? Researchers tried to find at least one uchastic of solid rock, but the result was disappointing. Almost the entire seabed in the construction zone is covered with loose deposits that have accumulated here over millions of years. This means that to create a foundation, it would be necessary to literally drill through these layers, trying to reach a solid base at an unreachable depth. Constant currents wash away these soft sections, creating voids beneath them. In Gibraltar, the ground itself turns out to be the most unreliable ally. Tectonic pressure compresses the space, earthquakes threaten destruction, and the unstable seabed refuses to support weight. Engineers have found themselves in a situation where they need to overcome the planet itself, which resists any vmешательство. And just when it seemed that the list of problems was complete, scientists conducted a final scan. What they discovered beneath the layers of silt ultimately pushed the project into the category of physically impossible. Are you ready to hear about the discovery that put a definitive end to the story of humanity's greatest construction? When the engineers' last hopes ran up against unstable ground, international research teams carried out a decisive scan of the strait. Scientists used ultra-powerful sensors and drilling rigs capable of operating at extreme depths. Everyone expected to find solid rock formations beneath the layer of silt for the foundation. But the results of the seismic analysis shocked the experts. Instead of a reliable foundation, they detected a massive layer of loose deposits that, by their properties, resemble a thick, viscous paste more than solid ground. Drilling confirmed that the seabed of Gibraltar is covered with a layer of unstable clay several hundred meters thick. Under the enormous pressure of water and constant vibrations from tectonic plates, this mass exists in a borderline state. With any external impact, such soil instantly loses density and begins to behave like a liquid. This phenomenon makes the installation of piles pointless. Any heavy support would simply sink under its own weight without meeting resistance. But where did so much soft material in the strait come from? The reason for this anomaly lies in the distant past. About 6 million years ago, the Mediterranean Sea almost completely dried up. When the natural dam in the Gibraltar area collapsed, the waters of the Atlantic rushed back with tremendous force. This ancient megaflood literally ground rocks into fine dust, which settled right here in the narrowest part. That ancient catastrophe formed the seabed structure that millions of years later became an insurmountable barrier for modern engineers. Today, the scientific verdict is clear. It is impossible to build a conventional bridge here. We have learned to create ultra-strong materials, but we cannot change the nature of the seabed, which is incapable of serving as a foundation. Any aggressive vmешательство in this system threatens large-scale underwater landslides. The project of connecting the continents remains a bold utopia that crashes against the geological reality of the planet. Gibraltar remains a place where natural forces set the rules, reminding humanity of the limits of its capabilities. If you enjoy stories about how nature challenges humanity's most ambitious projects, subscribe to the channel. Here,